Hi everyone, I'm Liliana Matos, Director of Front-End Engineering at 1stDibs. I'm joined by my colleague Rob Richard, Senior Director of Front-End Engineering. Today we will talk about defer and stream directives in GraphQL and how you can improve latency in your applications with incremental delivery. Before we get into it, a little bit about 1stDibs. We are an online marketplace that sells luxury items such as high-end furniture, fine art, jewelry, and fashion. Our front-end stack uses Node, GraphQL, React, and Relay, and our engineering offices are located in New York, Vilnius, Lithuania, and Bangalore, India. Before we talk about the why and the how, let's start with the what are defer and stream. Defer and stream are proposed directives to the GraphQL specification to support incremental delivery for stateless queries. We have been championing this feature since January, working closely with the GraphQL working group. In this talk, we'll discuss the motivation behind adding these directives to the specification, an overview of the specification proposal to date, code examples on how to use these directives, the current reference implementation in GraphQL-JS, our open source contribution to related libraries to support incremental delivery, and finally, some best practices for implementing this feature in your applications. Now, some of you may be asking yourselves, why do we need defer and stream? What problems do these directives attempt to solve? Well, one of the key disadvantages of GraphQL's request and response model is that large datasets may suffer from latency. In addition, not all of that requested data may be of equal importance, and in some cases, it may be possible for an application to act on a subset of that data. Today, there are options for applications, such as query splitting and prefetching, to prioritize certain data subsets, but they come with significant undesirable trade-offs. Defer and stream would allow GraphQL clients to communicate the priority of requested data to GraphQL servers without the trade-offs that exist currently. But before we delve into the specific of these directives, let's talk about the current options and their trade-offs. Starting with query splitting. Given a single query that has essential and non-essential fields, query splitting is a technique where you fetch these non-essential fields with a separate query that occurs after the initial query. While this approach allows you to improve the delivery time of the essential fields, it has multiple trade-offs. To start, it increases the latency for lower priority fields, now that they have to wait for the initial query to complete before starting the request. In addition, issuing multiple requests not only may increase contention on client resources, such as battery, but also can increase server costs in order to handle these additional requests. In the example, we're splitting out the non-essential field that fetches the picture of the speaker in order to optimize the delivery of the name of the speaker. This example demonstrates a particular worst-case scenario, where you have to request some of the data you already have in the follow-up query in order to improve the response time of the essential fields. Another available technique for reducing latency is prefetching, which involves optimistically fetching data based on predictions that a user will execute an action. Although an effective technique at improving or masking latencies by fetching data before it is needed, it has a significant trade-off of increased server costs due to incorrect predictions. Or we could use defer. The example in the slide demonstrates how using defer improves both the latency of the loading of the article as well as the user experience. A quick note about subscriptions before we move on. Subscriptions are a GraphQL feature that allows a server to send data to its clients when a specific event happens, but they don't fit the use case for defer and stream. The intention for subscription is for real-time and long connections, while defer and stream are for lowering latency for short-lived connections. Now that we've gone through all the reasons for why GraphQL needs directives like defer and stream, let's go over an overview of the current specification proposal for these directives. Starting with defer. The defer directive may only be specified on fragment spreads. It takes two optional arguments, an if argument and a label argument. The if argument works similar to skip and include, where if it is true, the fragment is defer, and if it is omitted, it defaults to true. The label argument, if specified, must be a unique label across all defer and stream directives in an operation. This label should be used by GraphQL clients to identify the data from patch responses and associate it with the correct fragment. Revisiting the speaker query we split earlier, instead of splitting this query, we can now add a defer directive to the speaker picture fragment. This allows us to prioritize fetching the name of the speaker without increasing the latency of the picture field and without refetching data we already had. Using defer keeps the query intact, allowing clients to build queries in a declarative way based on the needs of the application without compromising performance. Moving on to the stream directive. The stream directive can only be specified on fields that are of list type. It takes 3 optional arguments: an if argument, a label argument, and an initial count argument. The if and label argument work identically to the way they do for the defer directive. The initial count argument is unique to stream, and when specified, dictates the number of list items the server should return as part of the initial response. In this example of a stream list, we are asking for the first 3 speakers, expecting the first speaker to be returned as part of the initial payload since we specified an initial count of 1, and the remainder to be streamed. On the right, we see that the first speaker is returned immediately with the first payload. The subsequent payloads then return the name of the next 2 speakers. You may have noticed in the previous examples that the response format for the incrementally delivered data is a bit different than that of the first payload. Specifically to support defer and stream, the GraphQL execution will now return multiple payloads when an operation contains either defer or stream directives. The first payload is the same shape as a standard GraphQL response. However, it won't contain any fields that were requested on a deferred fragment and will only contain the initial list items for any list fields that are streamed. To go into more detail, the response format to support incrementally delivered data has several additional properties. The label property will be a string matching the label argument of either defer or stream if a label was present. The path property is a list of keys from the root of the response to the insertion point that informs the client how to patch a subsequent delta payload into the original payload. The hasNext property is present and true when there are more payloads that will be sent for a given operation. The last payload in a multi-payload response should return hasNext false. However, hasNext is not required for single payload responses to preserve backwards compatibility with GraphQL servers that do not support defer and stream. The data, errors, and extension fields are consistent with the way they are defined in the spec currently. The only thing to note is that the data and errors after the initial response are scoped to the deferred or stream field that is being resolved. Okay, let's pull it all together. In this example, we are streaming a list of speakers and deferring the picture fragment of a speaker from within that stream. On the right-hand side, the initial payload returns the number of speakers specified in the initial count argument, which in this case is only 1. The picture data is not present in the initial response because it is part of a deferred fragment. The subsequent payloads return patches of either the deferred picture of a given speaker or the name of the speaker in the streamed list. Note that the label that we passed in as an argument for defer and stream is present along with the defer and stream data. Also important to note that the path dictates where the data should be inserted for each patch. In this example, we're only asking for 2 total speakers, so after we receive the last picture URL of the second speaker, the last payload's hasNext property is false. One final note about hasNext. In some cases, depending on your implementation in your GraphQL server, you may not be able to know that the last chunk of data is the final payload. In that scenario, you would expect the last payload to only contain the hasNext property, and it would be set to false. Now that you have an understanding of how defer and stream work at a high level, I'm going to hand it over to my colleague Rob Richard to discuss the technical implementation of these directives and how you can leverage them in your applications.
Hey everyone, I'm Rob from First Dibs, and I'm going to talk a little more about the technical implementation of defer and stream. The first thing you may be thinking is how you can take advantage of these directives in your schema. I'm going to be talking about the GraphQL JavaScript implementation, since that's what I'm familiar with. Other servers may work differently when they implement defer and stream. Anyway, for defer, it's easy. All of your existing resolvers should work effectively. The GraphQL execution engine is going to fork its execution at the point where it encounters a defer, adding that tree into a dispatcher while it continues to execute the rest of the query. After the initial payload is sent, the dispatcher will monitor the status of each remaining execution tree. As soon as each one is complete, it sends the payload to the client. For the stream directive, you could use it on any field that returns a list type, but the way the resolver for the field returns data will affect how stream works. GraphQL-JS supports returning a few different data types on list fields. You could return an array or any other type of iterable, or a promise that resolves with an iterable. If you return one of these types on a field that uses the stream directive, you're handing the GraphQL executor all the results in the list at once. This is probably not going to send your initial payload to the client any faster, and all the payloads with the streamed list items will be sent immediately after that initial payload. GraphQL-JS also supports returning an array of promises. I think this is a pretty cool feature that not too many people realize exists. It could be useful for fields that you want to stream. When you return a list of promises, the GraphQL executor can wait for however many you specified in initial count for the initial payload, and then send each other promise to the dispatcher of subsequent payloads that are waiting to be resolved. The downside here is that you need to know how many items will ultimately be in this list when you return from the resolver. Here's an example of a resolver that does that. This pattern might make sense if you have an API, maybe one backed by a search database that returns object IDs based on a set of filters. Here we make a call to that search database to load matching item IDs based on filters passed in by the client. Then we map over these IDs, returning an array, and make a call to a different API that inflates items by ID. The return type here is an array of promises, where each promise resolves with an item. There may be some underlying batching and queuing here to load these efficiently. We're also adding the ability to return async iterables from list resolvers. You can write an async generator function to return your list items. These are the ideal scenario for list fields that use the stream directive. They allow you to load each item from your list asynchronously. You can also determine if your list is completed asynchronously after the last item is sent. There are a few ways to create async iterables, but I think the easiest is to use an async generator function. Here's an example of a resolver that is written using an async generator function. Async generator functions let you use the await keyword to wait for asynchronous data and the yield keyword to return that data to the GraphQL executor. If you set an initial count of 3 on your stream directive, the GraphQL executor will send the initial payload as soon as the first 3 list items are yielded. Each list item is yielded after that will be sent in a subsequent payload. Now I'm going to talk a little bit more about how GraphQL can incrementally deliver your data to your clients when you use defer and stream. You might be thinking of WebSockets or server-sent events, but those are not required. WebSockets require a stateful server to manage connections, and that usually requires complex infrastructure. Instead, we are going to stream data from a normal HTTP connection. And this works with most existing HTTP infrastructure and is supported in old browsers. We're going to use the transfer-encoding chunked header in the HTTP response from GraphQL. This is an old feature of HTTP 1.1. It allows clients to read a stream of data being sent from the server. The client does not have to wait until the entire response is sent. It can start acting as soon as the first chunk is received. We're going to combine our chunk-encoded HTTP connection with a multipart HTTP response. Multipart responses are a standardized way of encoding multiple payloads into a single request or response. It's commonly used for file uploads when you submit a form with files attached, and you'll also see it when you view source on emails with HTML and file attachments. We're going to be encoding the GraphQL response as a multipart response of multiple JSON payloads. Here's an example of a GraphQL query using defer and what the response looks like. Instead of a single request returning a single JSON object, we have multiple JSON objects. Each part of the multipart response contains a header indicating the content type. This format allows mixed types, but we only use JSON. There's also a content length header. This lets our parser know how many bytes to read before it can begin parsing the JSON. After the initial data is sent, the connection will remain open until each payload is sent. This is what it looks like when you make this request on the command line with curl. You can see how each of the JSON objects are sent over the same connection. They're sent as soon as the data is ready, and the connection is closed after the last one is sent. There's a proposed specification that the GraphQL working group is working on, defining how GraphQL should be served over HTTP. Most servers and clients already uphold best practices, but this will make sure there is a well-defined spec that everyone can follow. We're working on ensuring incremental delivery using defer and stream as part of this spec. This is an example of some Node.js server code to send multipart responses to clients. By using the response.write method, data is sent immediately using chunked transfer encoding. Response.end is called after the last payload is sent to close the connection. We have a pull request open to Express GraphQL to add support for this. Here's how you can read data from a stream in a browser. Modern browsers support the fetch API for fetching data. Fetch is an async function that returns a response object. Usually you call the async JSON or text function on this response object, but that waits until the entire response is received. Instead, you'll need to call the getReader method on the response body. This returns an object that has a read method, which will return a chunk of data as soon as it is received. Once you receive this chunk of data, you should parse it and return it to your GraphQL client so it can start rendering the data. You call the read method over and over until the done flag is returned as true, indicating the connection is closed and all data has been sent. Just to demonstrate that this is an old technique that does not require any modern standards, here's an example of how to do the same thing with the classic XMLHttpRequest API, and this will even work in Internet Explorer 7. So you don't need to implement all of this yourself. We built a library we call fetch-nultipart-graphal to support reading chunked multipart responses in any browser. It uses the fetch API, but falls back to XMLHttpRequest if fetch is not supported. At First Dibs, we use it with Relay in our network layer to support defer and stream. So that's all we have for you today. Here's a list of all the different aspects of the spec that we're working on. First is the GraphQL spec RFC. This is a high-level document describing the why and how of defer and stream. Next is our pull request of the edits to the GraphQL spec defining exactly how defer and stream should work. Then is our pull request to GraphQL-JS, which has the reference implementation. And we have a pull request open to add incremental delivery support to Express GraphQL. Fetch-nultipart-GraphQL is our client library to consume incrementally delivered GraphQL responses. And finally is the RFC defining how defer and stream should be delivered over HTTP. And that's all. Thanks for listening.
Hi, everyone. Thanks for listening to our talk. We have a few questions here already. So I'll start off with a question from Peggy. Her question is, are you using defer or stream in production at First Dibs? If so, how has the experience been? So currently we're not using defer or stream. We're actively working on some features to add defer specifically. We want to use stream down the road, but it requires a couple more infrastructure changes on our end to have it work efficiently. And really the challenge is you've written so many queries, so many fragments without these directives. And it's really kind of entangling things. And you could slap defer directive and have it work, but you really want to see those improvements in terms of like time to interactive. So we're just kind of experimenting and figuring out what fragments we need to defer to actually see some improvement from a performance standpoint.
Next question from Tim Ward. Can you elaborate on the reasons why defer is limited to GraphQL spreads? I know some early experimental implementations allowed defer on any nullable fields. Are there any constraints that the field needs to be nullable? So the first thing is we thought that defer on a fragment spread is more flexible than a single field. A lot of times you want to load several fields at the same time, and it can be complicated to manage the loading state of waiting for everything you need before you start rendering components that rely on them. So, and it's kind of easy enough if you just want a single field, you could wrap it in an inline fragment and defer that. So that kind of solves the use case. And unlike the experimental implementation, it's not necessary that the fields are nullable. So the GraphQL executor is kind of acting as if the field wasn't created at all on the first initial run. And then when you get the other fields back, so they don't need to be nullable. And are there any thoughts on how these directives can be incorporated, and if they should be, into proposed features like query batching? I'm not super familiar with query batching. I think it's how multiple queries get sent at the same time. And I don't think that there's any conflict with this. It's just defer and stream is network layer independent, and I think that the multiple batches could be sent over with deferred payloads without any problem. Do you want to get the next one?
Next question is from Hannah, and she asks, regarding defer and stream directives, would you be able to control when the subsequent payload will be returned, or only as subsequent payload is ready? You don't have control over when, at least coming from the server. The thought is the client would handle batching, so you don't have like a bunch of renders happening every time the payload comes in.
The next question, what use cases do you think make the most sense for stream? I think the most important use case is when you have a list of elements and maybe only the first few fit in on top of the fold of the page. So this lets you get those first few elements right away while the rest are loading. And that's why we support the initial count argument, so you could specify how many could fit on top of the fold. The next question, can I use stream directive to segment the payload into more parts? And so you could use the stream directive to segment the payload into as many parts as there are in the list element that you're adding the directive to. Next question, doesn't defer go against GraphQL's predictability promise? Client asks for a field, but it hasn't been returned by the server. So it kind of depends how you look at it. Well, the client is specifying that it's okay for this field not to be returned. So I think you're telling the server that this isn't a hard requirement, that you need this to render the rest of the data, and it's going to allow you to lower your time to interactive by doing it. And it requires more work to be done by GraphQL clients to make it seamless. And especially if you're using types on code generated types. So that will need to take account for that. Is Stream a good solution for sending video content or rich media that may be a lot of data that you don't want to send all at once? Our current proposal, I don't think is a good case for this. This is kind of specifically just a list of objects for GraphQL. But maybe there could be some way in the future to do something to solve that case. In the next question, the code examples included async iterators on the server. Anything preventing streamed GraphQL payloads being consumed as async iterators by the client? So actually in our implementation, when you call the GraphQL function, it's been updated. So it could, instead of returning a promise of results, return an async iterable. So when you're dealing with like the JavaScript API of GraphQL, it is async iterables. And it's just when you use the network layer, like something like Apollo server or Express GraphQL, that's when it gets turned into the kind of chunked transfer HTTP connection.
Next question, what was the use case that made you guys starting building these directives? Specifically, it was something very minor, but we have these little favorite icons on our search and browse page. And the way we get around it now is separating it onto separate queries. And it's something that would be perfect with defer, because you can defer this really small part and not hold up rendering the rest of the items. So we do get around it, but it's definitely the first kind of use case that we thought would really benefit from something like defer.
Is there any ordering involved when a query contains both stream and defer directives? So it's just up to, just as the executor is going through the GraphQL tree, it's going to hand off each part of the query whenever it encounters defer and stream. And there isn't any ordering. It's just whenever, as soon as one of those is finished, it'll get sent right away to the client. And how do you mark a deferred field as nullable? For example, if a field is non-nullable in the schema and I add a deferred directive, will code generators know that it's now nullable? So yeah, so a code generator would definitely need to know that those types need to be adjusted by defer and stream.
Next question, what's typically the most common challenge when refactoring to enable these directives? Logistically, what's challenging is being on a bunch of experimental branches. We're also, we use Relay to write a query, so we're also on experimental Relay. So working with that experimental framework and kind of just from getting these defer directives to actually improve your performance. Yeah, splitting queries, that's kind of what we've done. So when we've noticed something that wasn't performing well, we'd split it into its own query. So getting that back into the main query so you can actually defer it instead of splitting it out into a separate query. And on top of that, just like figuring out what you need to defer in order to actually see some optimizations versus just deferring for the sake of it. All right, that's it for us. Thank you, everybody.